Hey everybody, so today we're going to do a titration. So what we're doing is we're taking a known molarity of a solution, like you could use in this case, we're doing acid-base titration, NaOH, and we're going to use it to titrate another liquid, which is going to be, in this case, unknown, H2SO4. We don't know the molarity of the H2SO4, but we do know the molarity of the NaOH. That is, once we actually prepare the NaOH. So the NaOH that we're going to be using is going to be diluted from 6 molar NaOH. And we have a pretty general idea of how concentrated it is, but 6 molar is pretty vague. What we're going to use is the solid form of KHP, which is also known as potassium hydrogen phthalate. And that's going to be weighed out. Weighing it out will allow us to use all of the significant figures that you can hopefully get from a scale, depending on how precise it is, to figure out exactly how much of that compound per mole or per gram is in that sample. And you're going to have a few different samples to get an idea of what the concentration of the NaOH is through titration. So that sounds like a whole lot of information. We're going to go through that step by step. First thing we got to do is we got to figure out, to get to the right concentration of NaOH, which is definitely going to be less dilute than 6 molar, how much of the NaOH we're going to need to get what we want. So what we're going to do first is we're going to take the 6 molar NaOH and we're going to dilute it to 0.250 molar NaOH. Now the way that we'll do that is we'll use the classic MV equals MV calculation, or M1V1 equals M2V2, in order to dilute the solution. Now because you're working with molarity can be done in terms of liters or milliliters. The key is that you just make sure that you don't forget which unit you use in your calculation, because they're going to be proportionally concentrated. So all you have to do is set up the calculation now, and you'll end up with So once you take your calculation, you're going to line up all your numbers and just make sure that you have everything straight. V1 is equal to M2V2 over M1. And that's going to be equal to 0.250 molar times 500 milliliters divided by 6 molar. And it's important to remember that molarity is expressed in usually moles per liter. One thing that's a good trick for these kinds of titrations, which usually are working on the scale of milliliters, is you can actually recalculate that as millimoles per milliliter. And that helps a lot when you're going through some of the calculations with smaller volumes of liquid, or you could even do something as small as micromoles per microliter if you're doing a really tiny titration. No one really works on that scale. It just will transfer the math easily and make it a little bit easier for you in your calculator. As long as you use the same units of volume, you could use hectoliters, it doesn't matter too much. So let's punch this all in. So 0.250 times 500 divided by 6 is going to give us 20.8 milliliters. And that's going to be how much of the 6 molar NaOH that we're going to need to prepare the solution that we need for starting this titration anyways. Then we're going to standardize that solution, and we're going to use that standardized solution to do our titration of the H2SO4. All right, let's keep going. So what we're going to do now is we're going to take some of the 6 molar NaOH, and what we're going to add to this graduated cylinder is exactly 20.8 milliliters. So we have this whole volume. Just going to measure it out You should try to be careful, you should try to actually measure it out as carefully as possible. This is probably not the best container to use. It's a little bit big, but just be careful not to spill any of this NaOH in your eye. You want to get as close to 20.8 as you can, just so we are working with roughly what we thought we were. The main hazard of NaOH, by the way, that you should be very careful working with, is if it gets in your eyes, it can cause serious burns. So try to do whatever you can to keep it off your skin and to wash your hands with a lot of water if you get any on your skin. All right, so we have 20.8 milliliters. It appears, we probably have technically 21.2, so I'll make note of that. So I'll put the calculated and the actual. And I'm going to take this 1,000 milliliter flask. I'm going to just add all of this to the flask. It's such a less than precise device for measuring volumes. We're probably just going to add it quickly. Squirting out 500 milliliters through that nozzle would be pretty tedious. Don't want to go past the line though. This wash bottle alone contains about 500 milliliters. This flask is anything but ideal for this kind of measurement too, because the graduation for 500 milliliters, seeing the meniscus for that is going to be pretty tough. And also waiting for it to steady is kind of a nightmare. Just a little bit more. A little bit more. And it's good enough. So here we have our solution of NaOH, and this is what we're going to be using to do all of our titrating. So before we move forward, we're going to actually need to prepare our burette, and we're going to also need to prepare our KHP in our flasks. So KHP, we're going to be measuring out about 0.5 grams, and the key to making sure that we can carry precision to carry precision in our calculations, that is to carefully measure out to as many significant figures as possible the mass of the KHP for each individual sample. So we're going to have 3 samples here, and these 3 samples are going to each have their own number, because the amount of KHP inside of them will be figured into the calculations as the number of moles of KHP, and based on the number of milliliters of the NaOH that were placed into each of these individual samples, you'll have an individual amount of the sample that we calculated to be in here. What ends up mattering is the way that all of these calculations, whether you add a little bit more NaOH or a little bit less, all work out to correspond to the right amount of KHP. Don't spend 30 minutes at the scale trying to make sure you have exactly 0.500 grams of KHP, because you're just going to make your lab mates completely crazy. It doesn't really matter exactly how much of the water you put into this flask. Why? Mostly because when you put water in this flask, you still have the number of moles of KHP that are going to fully dissolve no matter how much water you put in there. KHP is a pretty soluble salt. If you had a less soluble salt, you might go with more water. More liquid, though, is going to prevent as quickly or as effective mixing as you could have with a more concentrated solution. So you don't want to have too much volume to be working with your titrations, or too little volume. I think 20 milliliters is a good way to go, especially we have a 125 milliliter flask. You don't want to fill this much up past about 100 milliliters. That's going to be the point where you're a little bit past any amount of the solution that you'd want. want to make sure that you're mixing effectively, quickly, making things easy for yourself. 20 milliliters. So once we have this dissolved by stirring, we'll be ready to begin our titrations. And that'll give us plenty of time to actually get started working on the preparation of the burette so that we have everything in place to get the titrations going. Once the burette is prepared, which has to be done in a very particular way, we'll take each of these samples individually, one by one, and titrate them, and we'll get into that when we get there. It's fun to watch this kind of stuff. Try to avoid any splashing onto the walls though, just because if you have too much splashing from vigorous stirring, you could lose some of your sample on the walls. And that's no good. Don't want to lose any of that sample. So when you actually begin your titration, you want to make sure that you're working with a completely clean burette. And it's good to actually put a little bit of water in your burette and give it a rinse beforehand. But the important thing about using a clean burette that you should realize is that when you clean a burette with water, you're going to be potentially diluting whatever you put into the burette once you begin your titration. So once I gave this a once over with a little bit of regular tap water, I'm going to make sure that I give it a rinse with DI water. DI water, as you recall, will have no dissolved ions in it, deionized water, and it will actually wash away ions that might be on the surface a little bit less effectively than tap water, but that's a different story. For now, you want to make sure you get at least a little bit of DI water over the surface of the entire burette to make sure that there are no extra ions that you're not interested in keeping around on the surface of this sucker. Then you're going to take a little bit of your NaOH, which I've bottled and labeled, as you should, and I'm going to pour a little bit of this into my burette. What I'm going to do first is I'm going to close this, the stopper, stopcock, and I'm going to carefully pour it just enough, just a little bit more. About 10 milliliters is fine. And I'm going to roll it around the inside of my burette. Being careful not to spill any of this, which is still NaOH, just so I coat the surface with the solution. The reason that we're doing this is primarily to coat the surface with what's actually going to be inside of the burette so that it doesn't get diluted by any of the water that might also be on the surface. That way all of that water, which would be diluting the solution, is diluted now and removed by this solution, which we're going to wash out. You also need to make sure that we pass some of this solution through the stopcock, and we allow the whole surface internally to get coated, and we finally have our clean burette ready to go. NaOH, especially at this concentration, is fine to go down the sink. All right, so we're ready to go on this titration. We have everything fully homogeneous in this Erlenmeyer flask with our stir bar. We've been stirring it for about 10 minutes at this point. And we have our burette, which is above the flask. So what we're gonna do first is we're gonna take a couple drops of phenolphthalein, add them to our flask. You don't want to add too much, but it doesn't matter that much. You just want to make sure that you have enough to see the color There's going to be so little of this in here that it won't really affect the concentration of the NaOH or the acid that's being titrated. So we have our NaOH. This is going to be, in this case, our unknown. We're going to know the volume of it though, which is going to help us calculate everything we need to know later. And we have our known, which is inside of our flask here. We have a known amount of KHP. And the mass is all we need to know because that's how much acid we've put into the flask to begin with. With that in mind, we need to make sure that we fill the burette carefully, and that means I'm going to take it to the side here so that I can fill it at a level that is close to eye level. You don't want to be holding the NaOH too much higher than your head. Let me just grab that real quick. Holding the NaOH over your head is going to be a very unsafe choice. Another important thing when it comes to filling the burette is you never want to go past any of the marked portions for volume. So you go and you see the markings for volume on the side of the burette. Never go past the 0. Once you're in uncalibrated territory, you're going to have a lot of trouble getting any kind of good precision in your readings. You also want to stay above the bottom of the burette, just because that's also uncalibrated territory. Make sure you don't have any drops stuck on the funnel. Pull it off and close your NaOH so you don't accidentally contaminate it. Another important thing about contamination is you want to make sure that you do the filling of your burette away from your sample of KHP, just because if you spill any of the actual NaOH solution in your KHP solution, let's say in the middle of your titration, you actually run out of the NaOH, you have to refill the burette. You should always make sure that you take the flask away so that it can actually not get contaminated in any way. You want to keep it as safe as possible because that could potentially affect your results. Next thing we're going to do is we're actually going to lift this up, get it in position so we can take our first reading. And the last thing you want to do before you're ready to go on any titration is you want to remove the bubble. That's very critical. If you don't remove the bubble, this volume in here is full of air, and that air can be compressed, it can affect volume, and that's not what we want when we're trying to take a specific amount of liquid that we're trying to measure here. We want very specific numbers, and if you have any kind of gas, it's going to affect volume. So, ions while use. Looking for my waste beaker here. You always have to keep a waste beaker handy. I'm just going to open up the burette stopcock really quickly, and that gas will come right out. Very easy to do. People mess it up all the time. All right, we are ready to go. So what you'll do first, as you begin, once you've removed the bubble, is you will take the first reading. So you want to make sure that you're always reading to 1/100th of a milliliter in this case. For this particular burette, that's what it's calibrated to. It's calibrated for plus or minus 0.10 milliliters. So you can expect it could be 0.1 milliliters over or 0.1 milliliters under whatever your reading is, but you want to make sure you collect all of those significant figures if you can. So that's going to leave us with, let's see, so 4.20 is going to be our first reading for our starting volume, 4.20 milliliters. We're then going to put your burette in position. Make sure the stir bar is working. You want to keep the tip of the burette just past the lip, just so that you don't have any kind of splashing problems, and it's far enough away so it's not going to be in the solution. But if you have to wash any of the solution down, it's also not going to get knocked out of the way. It's just a very perfect little spot where you just have to barely dip the Erlenmeyer flask to get it in position. All right, and then we begin. So the first time you do your titration, you're going to want to go a little bit fast and just see where you end up. So let's see what's going to happen here. So we got a little bit there. We'll just hold this right like this so you can see. I'm starting to see little flashes of pink when I drop the NaOH, and that's because the regions around where the NaOH is landing in the solution are a little bit more basic than other regions. So let's see what we've got here. Right now, we've used about a little bit less than 7 milliliters. We want to do our first run a little bit fast, mostly because we don't really know exactly what the molarity, we have an idea of what the molarity is, but we don't really know exactly what the molarity of this solution is. And we want to make sure that we know roughly how many milliliters to go for carefully on the next round. That way we can spend a little bit more time on the later runs making sure that we are extra careful. Also, don't be afraid to use DI water to wash down the sides. The DI water doesn't contain any base in it, so it's not going to affect your calculations. A little bit more. Looks like we're getting close because we're starting to get really heavy flashes of the pink, a sign that the actual titration is over, also known as the endpoint. Thankfully, we have a stir bar, which is helping us homogenize the solution quickly. One technique that is really good if you get close is, instead of actually adding a full drop, you can touch the side of the flask and you can wash down that drop if you're trying to be extra careful. Looks like it was, not enough anyways. Once that pink color is achieved, we'll be done. Let's see. So now we're going one drop at a time. It's good to have some patience with this. You don't want a deep purple color or pink color. You want a light pink color. This is even a little bit too pink, but it gives us somewhere to start. I'm gonna wash down all the solution on the sides, see where we get with that. But it happens super fast, so you want to be careful. Also, you want to make sure your wash bottle's nice and full. So this isn't ideal, it's a little bit too pink, but this is roughly what we're looking for. Lighter than this, the lighter the better. So now we'll look at our burette and we'll find our final volume. And volume in this case is 15.30. Actually 29. So we have an idea of exactly how many grams of the KHP. We know that's our known. And we have a rough estimate of what the actual molarity of the NaOH in this solution is. So the molarity will be calculated by using the volume of the total NaOH dispensed, which is going to be 15.29 minus 4.20. So the total volume dispensed makes for an easy calculation. It's going to be 11.09 milliliters. Our second sample, burette is ready to go. And we're going to add the phenolphthalein. Should have probably added it before I put it in place, that's fine. Put in 3 drops. And the last time I used about 11.09 milliliters. But if you noticed, we actually ended up with 0.704 grams of KHP versus 0.509. So this one's going to take a little bit more. Normally you can use roughly how many milliliters you used before to allow yourself to sort of skip past a few milliliters so you don't have to spend your time checking every single drop very carefully. And it'll help you speed things up a little bit. So we know it's going to be more than 11 milliliters for sure of the NaOH solution that we have in here, which is homogeneous, right? So let's get started. I knew I should have done half a drop there. Oh well. So this is what it looks like when you put a little bit too much base. And I got a little bit too confident adding the base a little too fast there. But if you have too much base, it's going to be more of this fluorescent pink color. And this is just a couple drops over, thankfully, so it should still be a pretty good reading. Now, when we look at the start volume for titration 2, we didn't take any actual base out of the titration or out of the burette from titration 1 to titration 2. So the starting volume for titration 2 will be the same as the end volume for titration 1. Usually you probably should record it though beforehand, as a matter of principle. So it's gonna be 15.29 milliliters. And if you look at the end volume here, you're sitting at about 30.99 milliliters. Just above 31, just a tiny bit. So if you look at the difference between those two, it's going to be somewhat proportional to the difference between the actual mass of KHP that was added to the flask in the beginning. And the math, as I mentioned before, will work itself out. If you have a little bit more KHP in this sample, it's going to take a little bit more NaOH. If you have less, likewise. It's going to work itself out in the math. The important thing is that you take as many of the significant figures as you can and record everything. Right? So let's see. Gonna end up with 15.70 milliliters here. That's gonna be the total volume dispensed. Add a couple drops of phenolphthalein. We are go. All right, 10 milliliters. So that's going to put us at about 10.74. So I'm going to hand drop. I'm going to touch the side of the flask and I'm going to wash it down. And that is what you would call the right perfect color. Very, very, very light pink. You don't really want it to be anything like this, which was just a botched example. This is the ideal color, just barely pink. So the final end volume for this is 11.81. 11.09 is really close to 11.07. That's what we got for titration 1. And it suggests that probably titration 1 and titration 3, which also had better color in the final map. It's just very barely pink. Still you can see, even maybe just a little shy of it. They are going to be probably the most accurate results that you should consider highly versus the more inaccurate result, which is going to be for titration 2. We'll see how the standard deviation works out. All right, so what we've done so far is we've taken some KHP, we've titrated that KHP with some NaOH solution that we prepared, and using calculations, we actually can figure out what the concentration of the NaOH solution is. Once we have that molarity, we can apply that to virtually any acid solution that we find. So when we have H2SO4, let's say an unknown solution, we don't actually know what that concentration is. And we have to go a little bit more carefully in using that NaOH because we don't know if it's going to take a little or it's going to take all of it. In that case, we're going to err on the side of using a little of the NaOH, and we're going to take some small samples of the H2SO4 and see how that goes. So first, we're going to go for about 5 milliliters of this H2SO4 solution, which I've already placed in this burette. And we're going to do it just like the other titrations. I'm going to add a specific aliquot of the H2SO4 solution. So I'm going to actually record exactly how much. So for aliquot 1, or for sample 1, you'd measure this just like you would measure the other samples with a start and an end volume. Trying to get as close to 5 milliliters as possible, but the actual volume is what matters. So don't stress so much about the 5 milliliters. So now we're going to get started with the final titration, which in this case is a titration of the sulfuric acid, H2SO4, and it's an unknown concentration. So in each of these flasks we have 5 milliliters of the unknown sample, which I measured out before. And all we're going to do is we're going to add a little bit of water just to increase the volume here. So I'm going to add about 15 milliliters to each of these flasks. Next, before the titration, I'm going to check to make sure there's no bubble. I actually didn't change the burette at all between these titrations and the ones of the KHP, so it's just like we left it, including the final volume, but we'll re-record that in a second. And I'm going to add a little bit of this phenolphthalein just to get us some indicator concentration in each of these while we're at it. So 1, 2, 3, 1, 2, 3, 1, 2, 3. Indicator will change the same color, so we're always aiming for that light pink color, not for that really bright, intense fluorescent pink that we saw in sample 2 last time. Just a little swirl, a little rinse. We're ready to go. Oh, this is 3, so I'll start with 1. Remember, you don't want any of the sample that you're trying to titrate to end up on the sides, so you always want to wash down with DI water regularly. So this is a little bit high. I'm going to just adjust this or a little bit low. Adjust it a little bit. There we go. And I'm going to take the first recording. I'm going to take that first recording as 11.84 as the starting volume. Usually when you're doing an unknown that you haven't tested yet, you want to start with as much volume as possible and kind of take a walk on the wild side here. We still have about 40 milliliters left, so we should be fine. Let's get started. The real warning sign is when it starts to persist in color, which is getting closer to. You want to move to the drops instead of allowing a stream. Now it's really starting to get persistent, so let's see if we can get it at exactly the right color. One more drop. Oh, that was dangerous. See, you got to be very careful with your hand there. And oh, that's how quickly it can change. Just 2 drops. Wow, I really did it there. So at least this was the first one. It was rough, like I mentioned before. Let's take the final volume here. Doing this on camera is a little harder than doing it normally, that's for sure. 25.88. Milliliters. And you're gonna end up with roughly, let's see, 14.04 milliliters dispensed there. Now each of these samples had exactly or very close to plus or minus 5 milliliters or 0.05 milliliters of the sulfuric acid added. So we can safely add about 12 milliliters to samples 2 and 3 before we have to really start getting very careful about how much we add and how fast we go. So I'm going to try to run through these and see if I can't do any better. This was pretty pathetic, not the right kind of color, so we'll see how we do. That's good. So by comparison, these 3 are not extremely good samples. The last one came out pretty well. It's very, very faint pink. You can only see it against the white. And usually it's good to keep a piece of white paper underneath, especially if you don't have a stir plate handy. These are only a couple drops past where they're supposed to be, and they'll still be quite precise. The calculations will work out well because, especially for this one, we actually recorded it at the earlier volume for the final volume. That'll end up being closer to the real final endpoint that we're more interested in. If you're just on the edge, plus or minus 1 drop, it's still plus or minus 1 drop, so you're actually going to have good numbers. You shouldn't worry so much about the endpoint because it's actually a little bit further than the technical equivalence point. Usually the pH of phenolphthalein when it changes color is a little higher than 8. So when you actually want to calculate the final concentration of H2SO4, what you're going to want to do is you're going to want to first go through the KHP titrations, look at what the concentration was for the KHP and what the resultant concentration that you found for the NaOH would be, and then use that NaOH, now that you have it as a known concentration, to solve then for the H2SO4 concentration based on the 3 titrations that you did. Once you do that, all that's left is the rest of the post lab and you'll be done. And like I said before, you could do this with virtually any acid, or you could fill this with acid and do it to a base using a different indicator. It just depends on what kind of application you want to use with titration. If that's all, and it is, then I will see you later.